Okay, so this is a quick video to explain forces. We're going to look at resultant forces on stationary objects and moving objects, and we're going to see Newton's second law. When the forces are unbalanced, what happens to the object? So keywords here are resultant, Newton, because he had different laws, acceleration, mass, and stationary. Okay, also balanced forces and unbalanced forces. Okay, so here's like conservation of momentum. This lesson explains the various effects of forces on motion, and the main focus will be looking at the difference between balanced and unbalanced forces. So the ancient Greeks, Aristotle, thought that for an object to continue moving, there must be a force making it move, acting on it all the time. So, what was wrong with it? What couldn't Aristotle work out? Well, can you think about that? In 17th century, Galileo came about and he argued that objects keep moving unless acted on by a force, for example, friction. So the ancient Greeks didn't really think about the friction, which must be taken into account as a resistive force. If we go into space, we can eliminate friction, air resistance, and there we can study what Newton came up with. But Galileo was correct in his thinking. So then Newton encapsulates what's happening when there's no friction. It's easier to see. So here you've got an astronaut in space in a spacesuit, and of course, without a spacesuit, he wouldn't survive in space due to the very low temperatures, and the fact that there's no pressure means that he needs a pressurized suit. Otherwise, his cells would explode from inside one by one. Anyway, that's irrelevant for now. So here the astronaut is holding a red ball. So if Aristotle's idea had been correct, this is what you would see happen, because look what happens when the astronaut lets go of the ball or pushes the ball away. If Aristotle was right, then the ball wouldn't be able to continue moving, and it would stop because the force on it was only momentarily in action when the astronaut pushed it. However, Newton explained motion better. He said objects continue to move in a state of constant velocity unless acted upon by an external net force or an external resultant force. Okay? So if you do the same action again, the astronaut pushes the ball should continue in its constant state of motion at constant velocity. And because in space there's no resistance, it will just keep on going forever until something happens, like it enters a gravitational field, or enters an atmosphere of a planet. Then there will be other forces acting. So that's Newton's first law, and it's also true if the object's not moving, it will continue to not move because it's the same, it's just the constant velocity would be zero. Okay? So obviously in space you've got to be careful, because not having any friction can also be dangerous. Oh, there he goes. Someone's snooker cue knocked into him, and he's now going to continue moving in that direction forever, and how will he be able to get back? Okay, just a thought. So Newton then also said that every action has an equal and opposite reaction, and this is actually his third law. So we've missed the second law for now, and the third law, if he pushes the ball one way, that will create him a force on him which pushes him back the other way. Now the ball moves off with greater velocity because it's less massive, and that explains exactly why guns recoil and how rocket engines work. So you've got to send some mass in rockets out of the engines at the back, which makes the rocket propel itself forwards, and it's part of Newton's third law which does that, which means that the momentum of the ejected gases at the back of the rocket one way creates an equal and opposite momentum in the other direction, and that's explained by Newton's third law. Every action has an equal and opposite reaction, and those of you who've done my course in school will know that that also means that momentum is conserved in the process. So coming back to see the astronaut do that again, at the beginning the astronaut and the ball are stationary relative to each other, so you could say their total momentum is zero. Neither of them are moving with any velocity relative to each other. Then the small mass, which is the red ball, will move with a velocity to the right, and the astronaut with a bigger mass will move with a velocity to the left. And if you multiply the mass by the velocity of each object, the magnitude of the velocity times the mass will be equal in both directions. Okay, hope that makes sense. That's Newton's third law, and it links in well with momentum conservation. Okay, so another example of the third law is if the astronaut is moving forwards and he wants to stop, what can he do? Well, he could throw the ball forwards, and that makes him reduce his momentum forwards. So that will hopefully allow him to stop if he gets just the right momentum on the ball. Okay? Of course, a better way would be that he has a rocket on his back, a small rocket that will allow him to propel himself in various directions by ejecting mass out of his rockets. Okay? But if you throw the ball too hard, you could be lost in space forever, which again is why I always say, if you're working in an international space station and you've got to do a spacewalk, make sure you have a rope that tethers you to the International Space Station, because if you push off it, Newton's third law means that you will move backwards and you won't be able to get back at all. Okay, now here we have looking at different forces acting on one object. So if the drive and the drag are equal, the car will move at constant speed because that is Newton's first law. Okay? Newton's second law is when the forces are unbalanced, and when the forces are unbalanced, there will be some acceleration. So balanced forces, there's no acceleration, no net force, no resultant force, another way of saying it. So no acceleration means no change in speed. As soon as one of the forces is bigger than the other, so if the car was accelerating forward, then the thrust forwards, or the drive force forward, would have to be bigger than the drag force backward. Okay? So once again, if the thrust going forwards is equal and opposite to the drag force backwards, it will just drive at constant speed. Okay? But if the drive was greater, you could actually accelerate the car forward. So we're going to look at what happens in different scenarios to when forces are balanced or unbalanced. Okay, so here's another car driving along a road. What happens when there are unbalanced forces acting on the object? This is when Newton's second law applies. So Newton's first law is about balanced forces, and Newton's second law is about unbalanced forces. So when a driver who is traveling at constant speed accelerates by pushing on the accelerator, or he puts on the brakes, then you have an unbalanced force acting on the vehicle, either to speed him up or to slow him down. Okay? So there you've got the drag pushing backwards and the drive pushing forwards. Right now they're equal, so it should be going at constant velocity. If the drive is bigger than the drag, then it will accelerate, but if it accelerates, the drag will get larger because the drag is related to speed, and the speed will increase, the drag will increase, and eventually it will reach a terminal velocity or a maximum speed that it can go with that engine force pushing it forwards. So eventually a moving object, the drag will build up until it equals the driving force. That's why cars have a maximum speed, or any moving object will have what's called a terminal velocity. And we looked at that when I did my course on forces with a skydiver jumping out of the plane. At first the weight is pulling him down and accelerating him. Eventually the drag force will equal the weight and he will reach a maximum speed. If the brakes now are bigger, or the drag force is bigger than the drive, so if you take your foot off the engine, off the accelerator pedal, the air resistance or the drag force will slow you down because the reverse force was momentarily greater than the drive force. Okay, so that's again, so if you want to see it again, drive force greater, accelerates, drag force build up, constant speed. Okay, then when the braking is greater, drag force is bigger, they then become equal, and it goes back to constant speed again. I should say constant velocity. So resultant forces, here's a little test for you. Situation 1. So what is the correct answer with the force diagrams shown? Reaction is the name of the force when an object, such as the car, is pushing against the floor. There is a pushback from the ground, and that's called a reaction force in solids. Now you can see there's no drag force and no drive force, so what will the car do? In this case, the forces on it must be balanced, so the answer is stationary, because how do we know that it's not moving? Yeah, the resultant force is 0 and the car is stationary. If it was moving, there must be a drag force, because any moving object creates a drag force. What about situation 2? This time you've got 4 forces acting on it. One forwards, one backwards, one up and one down. And the length of the arrows indicates the size of the force, and if the length of the arrows in opposite direction are equal in length, then the object will be balanced in those directions. So what's the answer in this situation? Is the car A, stationary, B, moving with constant speed, C, accelerating, or D, decelerating? Okay, so you should think of your answer now, and here is the answer. It's moving at constant speed. How do we know? Yeah, there's a resultant force on it is 0. All the forces are balanced in opposite directions, and the car will continue to drive at the same speed, or a constant speed, in the same direction. So same speed, same direction means E is same velocity, because velocity is the vector quantity of speed, where it explains a little bit more. It can be represented by an arrow. What about situation 4? Situation 3 doesn't seem to exist. So situation 4, what do you notice about how this one is different from one before? So is the car now going to be stationary, moving with constant speed, accelerating, or decelerating? Okay, give you a moment to think. The answer is coming up now. So it's accelerating because the forward arrow is greater than the reverse arrow. The thrust of the engine is greater than the drag on the back of the car. So it must be accelerating. So this is a situation where Newton's second law applies. Unbalanced forces creates an acceleration. And because it's forward, we call that a positive acceleration. And the acceleration is always in the direction of the resultant force. And resultant force means take away the smaller arrow from the bigger arrow, and the leftover length is equivalent to the size of the force. Okay, in this case, this should be situation 4, and the last one should have been labeled situation 3. In this case, you'll notice the opposite. The reverse arrow is greater than the forward arrow. The up and down arrows each time have been balanced, because obviously when the car's weight is pushing down the road will react to equal it, unless the road can't take the weight of the vehicle, but I don't think that will be the case on most roads. Okay, so what's going to happen in this case? Is it going to be stationary, moving at constant speed, or accelerating, or finally, will it be decelerating? The answer is decelerating, because the reverse force direction to the motion of the vehicle is greater than the force forwards, so the car will slow down or decelerate. Okay, so I hope you found that useful. Here's some things you could try to test yourself with to make sure that you've got all these points for yourself, and make sure you got notes on all these before you do your test on forces and motion. Okay, well, thank you for watching the video. I'm going to upload this to YouTube for you. If you found it useful, please like it, share it with any friends who are doing the same course as you or in other schools, and make sure you subscribe if you want to know when the next video is uploaded. Thanks for watching. Bye for now.